So today we're going to look at some other constructs of the language, so loops and conditional statements, and also functions. And then we will go into numerical programming as well. So before we do loops or go into these statements, we need to look at how Python structures code. So in Python, there is no notion of curly brackets or begin end or that you find in other languages. So the code is grouped by indentation. So for example, here we have a loop, a for statement. And you can see here there's a colon at the end. And that tells Python now there is it expects a new code block. Now the code block is indicated by indentation here. So if you have a text editor, you can set indentation of 4 characters, for example, and you just tab it in and get indentation here. And it's also important that you have consistent indentation, so that you don't have 5 characters somewhere mixed with 4 characters in the same block. It has to be the same. Otherwise, you get really strange errors of unclear indentation and stuff like that. So here you can see here I have a for loop, and in the block that belongs to the for loop is the print statement here because it's indented. So a code block always starts with a colon, and then next line is an indentation. This line here does not belong to the code block, so that is a line that is outside of the code block for the for loop. So running this here, you can see that it loops over execute the print statement 5 times, and then prints this statement here. So if I would have done this, you will get this instead. So now all of a sudden the print statements that I had at the end belongs to the code block for the for loop. So indentation matters in Python. So then we can start with loops. So the basic loop statement in Python is the for statement. And you can loop over a certain number of times with a loop variable. Then you have for I, for example, in range 10. So the range function generates kind of a virtual list of items that you want to loop over. So it's not an actual list, it's a range of values. And 10 here is the less than value. So 10 is not included in the list. So the sequence is from 0 to 9. So up until, but not including 10. Like that. You can also set a start value of the range. So the first parameter here can be a start value, and the second is the end here. So in this case, we start from 5, go to 10, because we set 11 here. So 11 will not be included in the range. And you can see it starts from 5 and goes to 10. The third parameter in the range is the step. So here we start from 5, we go up until 20 with a step length of 3. So you can see it skips over here. So this is kind of the classical loop that you can compare with other languages like C and C++ and Fortran, where you have a loop variable and you have a range. The thing is that you can also iterate directly over data structures in Python. And you use this basic same construction here. You have instead of having a loop variable that is the index, you have a loop variable that is actually the value of the current position in the container. So I have a list here of values, and I want to loop over them. And in loop variable, I set value here, and then the in operator and what data structure I want to iterate over. So I don't need to know any indexes here. I want to loop over all elements in the list. So this also prevents you from specifying the wrong range. It will always loop over the exact number of elements in the list.
So instead of value, we can write whatever.
Yeah, you can put v here or x, but x will be the value in the list. And you can also, if you want to have an index, it's also possible to do that. So, for example, I have a list here with some character strings, and I have a B list here with values, and I want to iterate over both of them. One way is doing the classical one, is that you do for I in range, and then you use the len function here to query the length of A, and then you create a range from that, and then you have an index variable that you can use for accessing both of these lists. So this is the clumsy way of iterating over two lists. You can also do using something called enumerate. So I have a list here of values. I want to iterate over it, but I would like to have an index that I can use for accessing other stuff. Or if you have multiple data structures, you can get an index here. So then enumerate will actually give you an index and a value from the list. We can actually do something like this as well. Print, or do like this. So you can see what enumerate actually, the structure of that. You have to convert it to a list, otherwise you get the object, enumeration object. But you can see here you have pairs of 0, which is the index, and then the 4, which is the value. You can also iterate over 2 or more lists automatically without any indexing, using a kind of strange function name called zip. So in this case here, in the zip statement, you give all the lists that you want to iterate over, and on the first part of the for statement here, you give the variable that should represent each item in each list. So in this case, x will be a value in the xpos list, y will be a value in the ypos list. And here also I show you how that structure looks like. It's very similar to enumerate, but enumerate will generate the index for you, but zip will combine 2 lists together in pairs like this. Yeah, if you have 3 more, it would be kind of triplets. So this is a good way if you have multiple things that you want to iterate over in a loop without complicating indexing. You can use the zip function. Then you can also iterate over nested lists. So for example, if you have, here I have points here. So I have a list of lists. So every point here is a list inside an outer list. So I can use kind of constructed example here, but 4 p in points. That will be the outer loop that will loop over these lists here. Then I have an inner loop. You can see that I have a code here, and I have an indented block here with a for loop over the chord in P. So this P will give me one of the points, and then I loop over, I name that each value here is the chord variable here, then a free chord. So you can see it just linearly goes over everything here. 50, 50, 130, 70, and so on. But here you can see you have the outer loop block is this one here. So that is the loop part here. And the inner code block for the inner loop is this part here. And you can see the indentations here. This is the first indentation. This is the second indentation for the nested code block. I think you can't mix within the same level, but I think you can have 4 and 2 if you're consistent. But I wouldn't recommend it. You can really complicate error messages from Python that you really doesn't make sense if you have that wrong. So you can also use, I mean, it can take tabs and spaces, but yeah, this is also a religious fight here, which use tabs and spaces here. But I usually do only character tab spaces for Python, because it's really it's complicated looking at the code with tabs as well. So yeah, but it's the important thing, you need to be consistent. You can iterate over dictionaries as well. Then you can have key value in name dict items. So you have key value. So then you get the key and the value over the dictionary. So a dictionary has a we can print that out as well later here. It has a items property, or a function that returns you the items in the list, and we can just print them out just to see what it is. Name dict. So here you can see you get the list of pairs of values in the dictionary. Then you can also, if you only want to iterate over the keys, there is also the keys function here, or method of the dictionary, which gives you only the key. And then you can use the key to access the dictionary itself to print it out. And if you're only interested in the values in the dictionaries, you can use the values property just to kind of print them out one by one. As well, if you're not interested in the keys, just the values inside. That is also one way of doing it. So the for loop is kind of the main tool for iterating over data structures in Python. There's also, if you want to do iterations where you have a condition that you want to loop until a certain condition, you can use the while statement. And it works like you have while, and then you have a condition that has to be true for the loop to continue. And you see it's constructed the same way. You have the while statement, a colon, and then you have a indented code block here. And that will continue iterating until this is fulfilled. So let's see if it works. It prints out a lot and it stops here. So that is iterating. You also want to work with conditional statements, so if statements and logic constructs. And in Python, you have if. Same kind of basic idea. You have the colon, indentation. So this code block will be executed if the condition here is true. Then you can nest them as well. So you can have else statement here. You can have if. This will be if it's true. Otherwise, this will be executed. And you have also the elif. If you want to have multiple conditions to test for, you can do if, elif, and then if nothing else is filled, you do else here. Nested if statement. So this is for the true statement, else, and this is the code block for the else statement. So you have this if statement will only execute if this condition is true. And you can see you need to work with indentation here to make it work. Another thing that sometimes can be important is controlling the loop iteration. So if you want to break out or continue to the next iteration statement, you can do that using two statements called break and continue. Break will terminate the loop and exit and continue after the code block. Continue will go to the next iteration. So let's run this one here. So you can see here if I loop with 20 iterations. If I is 10, I break. So I exit the loop here. This is this statement here. And I go to the next iteration here when I equals to 5. And then I print out. So when I equals to 5, this will not be executed. It will continue to the next one. Sorry, what is it? It depends on your algorithm. So if you want to, for example, if it comes to a conclusion before this here, you don't have to do the complete iteration. So break will go outside here directly. And continue will just go to the next iteration.
And do you understand why you would write that? I mean, you would do it anyway.
Yeah, it's the break I can see for but continue is I'm not sure really. Depends on how your code, your own code looks like. Otherwise, it could be that if you have a lot of if statements operations after this, and you know that you don't need those, you can skip that execution and just go to the next iteration. So it can make the code more efficient, but it's also makes it more hard to read because you kind of it becomes a bit about a spaghetti. You have too many of these. So then there is a small task here. So you can see if you can find errors in this code. So I think I have copied that code into this code block here. So if you run this here, you can see you get some problems here. Now you can see that there is unexpected event. So it did something here, and you see there is a for loop here with a print statement. There is an extra space here. So that is our first error. And then you can see here that we have a for loop here, but there is no colon here. So that's what it said that the syntax error actually, it expects to have a colon here, but there is none. And we have more errors here. So parentheses was never closed. You can see here right here, and there is no parentheses here. The Python will stop at the first error, so it won't show you all the errors until you kind of fix them. So now it worked. I'll just copy that back here. Then we have a for loop here, or a list which we want to iterate over. If you want to try it yourself, or you just want to listen to me. First thing we do is we copy over the list assignment here. So if we just want to print them out, we can do for B in L. That's one way to do it. Let's see what I have here. Yeah, almost the same. Functions and subroutines. So up until now, we have just kind of written code up right in a source code file, or we haven't organized it anyway. And one of the important things in programming is to kind of organize your code in logical blocks. And to do that, you use functions and subroutines. And in a function in Python, there is only one type of function in Python. If you want a subroutine that doesn't return anything, you still define a function using define statement. And it works like it starts with a define, and then you give the name of your function like this. And then you give it a parenthesis. And if you don't have any parameters, you have to give an empty parenthesis. And then the same concept as for the for loops, you have a colon. And then the code belonging to the function will be indented. So this part here, the print statement, belongs to the function. And if you execute this, nothing happens, but the function is now defined in Python, so you can use it. And you can then call it using just print here, like that. If you want parameters, you can list them here. Just give a parameter list in the parentheses. this, and then you can use this as a normal variable inside a function. And here you can see here, I don't give a type of the variable. So if I want to print it out, I need actually to, this is the kind of safety measure, I convert it to a string. And every variable in Python can be converted to a string. So this will print it out regardless of the type. So here to use it, I call b. I'll define a b variable, and then I call the function with the b variable. So the variable name, parameter, argument to function doesn't have to be the same as the variable here. So you can see it printed out 42. So it goes in here into the function and we used here. So I can also do, for example, 42.0 here. You print it out, and I can also do a string. Still work. I can even do a list here. So it can print it out as well. So if you want to change the variable that comes in, so one idea, you do like this, a print function here, and you just a equals to 84. So any idea what will happen here? Will it print 42 or will it print 84? Yeah. Print 42. Yeah. Yeah, it printed 42. Yeah, so the thing is that this here is so 42 is stored somewhere in memory. We pass it over, it prints it out here, 42. So A points to the same memory location as B here. A here actually redefines incoming variable. So this one will create a new memory location 84, and A will, inside this block, it will point to 84. But coming out here, it will not affect this here. So you can't pass variable values out with assigning the input argument like this. You need to do something else. So that's why it printed 42 here, because it's this is just an internal variable here inside the block, and it just goes away afterwards. So all arguments coming into a function can be used as variables. So you can also change them inside a function, but it will not affect the variables outside. So you can use lists is a bit an exception here, but for the most part, arguments coming in cannot be modified inside a function. If you want to have values coming out from a function, you can return them using the return statement here. So this is a kind of classical mathematical function f of x, return c of x. We also do from that. This does Python interpreter to import the functions of the math module and make them available directly in our code context here. And also you can return multiple values from a function. So x, x divided by 2. Let's see here this. And also you have to receive them like this, x, y equals to test 42. And now I come to the exception of the rule here with you can't modify things inside a function. So let's see here, we have a list here A with numbers in it. We have a function modify list B. So B is coming in here, and then we do B0 equals to 42 and modify list. So what do you think happens here? Will A be modified? No? Yes. So A now points to the list in memory, and we give it here. Now it's called differently, but B now points to this list here as well. So if we modify 0 here, it will modify the data structure here that's in memory.
So basically, value that we put inside the function in this scenario be like an example for it's like an example, right?
Yeah.
For the whenever we apply the function.
Yeah, it's just that you can. It's possible to modify if you set a list into a function. It's possible for the function to modify the list that is outside the function here as well. So if you send in scalar values, it's not possible to change them inside the function. But if you send a list here, you can change the values inside the list in the function. But you can't do like this b equals to like this. That will not change the function, the actual list coming in. So this will just redefine the b that comes in here. Now it points to this structure here. When I do this, now I point to a different list somewhere else, which is actually only local to this function. So, but this is okay because I just modify the internal part of this list. I tell you this now because that's something that has been, when I started using Python, I learned it myself, and it was kind of confusing what was happening here. So I just kind of give you the example what's the behavior of Python in this sense. But this can be useful sometimes if you want to process something. You can send a list over and you can process the list inside a function, which is kind of useful. Okay. Now you can modify it in place. So I come from a kind of compute background, and if you want to return it out, it usually means a copy, and that is really bad for computational performance. But for other things, it's not bad. But it's kind of confusing in this sense because first you say that you can't modify the values coming in, but then you have lists that can be modified. And then we will go into NumPy arrays that actually work a little bit what you do in Fortran and C when it comes to memory allocation. It tries to avoid as much as possible copying of anything because it's bad for efficiency. So yeah, you should. I always just say you should try to avoid side effects if you can. But for performance, sometimes you need to do this. And in Fortran, for example, everything you pass to a function by default is referenced. So many functions, they modify things coming in just because you have data structures that are large and you need to modify them inside. So you can try yourself to implement this function here in Python. So this function should return the value of the expression. You feel ready? Okay, so def, we start defining a function, and then we give it a name, parentheses, and we have only one parameter here, x, and then a colon. And you see here that our notebook is it helps us to do the indentation here as well. So then return to actually return something out of the function. And we have 2 times x, 2 plus, let's see, 2x plus 3. Oh no, I have to test it here as well. I just print. So define f and then the parameters, colon, and return to return something out of the function. You could also have done y equals to f of 0, for example. That is also okay. So then y will be the result of the function. Did I do right? Yeah. Yes. So now we have our basic building blocks of Python. And now we would like to organize and use other building blocks, your own building blocks or other building blocks. So in Python, there is a large runtime library. And if you want to access those modules, you need to use the import statement. So for example, if you want to use math functions in Python, there is a math library called math, which you can import using the import statement. And when you use the import statement, it imports the namespace math into your code. So then you have to use the math prefix to actually access a function inside this module. So math.syn and math.py, which can be a bit, it produces long expressions, so to speak. You can import modules in different ways. And one other way, if you want to have functions, all the functions of math available to you without the prefix here, you can use from math import star. You can also, the star can also be replaced with specific functions from that module. So from math import star. And then you can use the math functions directly like this. And as I said before, you can do explicitly certain functions only. Using the star operator takes more time. So it could be more efficient sometimes if you just want 2 functions, just to import some of them. And one problem with this approach here is also that you can pollute the namespace in your code. For example, we will discuss in the next hour a library called NumPy, which is an array computing library, which provides all these functions as well. So if you do from math import star, and then you do from NumPy import star, those will be overridden. So the old functions will be overridden by new ones. So it's encouraged not to do that, but I will show you how that can be done in a way, in a different way. Also, if you can create your own modules, and it's actually really simple in Python. Any source code file can be used as a module. So if you put functions in a source code file, you can import it as a module. And you import it by giving its name without the extension. So the source code file has, for example, prime.py, and be imported by the import prime. So in this way, it's really simple to organize your code. Just put it in different files and then import them. And here is an example here of a module, prime.py, and it contains a single function here, is prime. It imports math, the square root function here. This is just to be able to, I do it every time to make sure that we can use international characters in the source code. Like this. So we put it in a single file. Now it's really a bit hard to simulate here in the notebook here, but what I'm doing now is actually downloading the prime file into my book here. So this is just, if you run it standalone, you just create an empty file with the contents here. I'm just downloading it from GitHub. directly. So it's available. If you look in the file folder here, you can see I have a prime.py file. And to use that, my module now, I can do import prime. When I do that, it's available. So now I have had a print statement, I'm thinking that, or not, okay. I'm not sure why I printed it. But you can use the functions in that module by prefixing here. Prime is prime. And you can do that. So now that is available to my code. So this is a way of modularizing your code. And if you have I encourage you to kind of use the normal import to kind of identify what is your functions from which modules. If you do mathematical expression, it's sometimes better to have a short prefix or no prefix, but for larger modules, it's better to have this prime.
It would be possible, yeah, for import.
Yeah, you can do a from prime import star as well.
Yeah, that is fine.
Yeah, then you can do just is prime. I can also show you here, you can do, for example, if you want a shorter import, you can do, there is an as part here as well. Import as prime, for example. So you can shorten those. And that is the default way of, for example, importing NumPy, which I'll come to later here, is you do import NumPy as MP. So to get a short prefix that still identifies the module somehow, but it makes the code more readable. But you can also do from prime import is prime, for example, or star. It looks in your current folder. You can set the Python path where it looks for modules. You can also put subfolders as kind of submodules, but you need to put a special init file inside your folder to make it recognizable by the import. Yes, I can't remember exactly, but you put a dunder file with 2 underscores and inside that folder, and that will also be as a kind of virtual module. Main program. Yeah, so, sorry?
With this import, you can only import like Py files and not notebook files.
No, it has to be Python files.
So you have to export from the notebook to.
Yeah. And my recommendation is to, when you write code, larger parts of code, don't put them in notebooks. Put them in Python file, module files. Then you can use them as normal Python code, but you can also import them in a notebook. Because if you run a notebook and you have Python files inside the same folder, you can use import there instead. And it's much easier to maintain your code that way. But actually, import can also import binary modules, which we'll come to later in the course. So most of the runtime library in Python is actually not Python code, but C code. So there is a way of generating bindings for Python from C, Fortran, and other languages that makes them, those modules as easy to use as the Python modules. And most of the functionality in Python is C because of performance. So if you can find a function that does something in Python, that is good. If you have to iterate, it's bad. Unless, so if it's large iterations. So if you can use functions, that's why NumPy was invented, because you want to do matrix operations in C because it's faster. So another thing I will talk about is, I mean, Python doesn't really have a concept of a main program. So you execute the Python interpreter and it's on a script, and that script kind of is the entry point of your code. Now you can start any script, but sometimes you want to be able to use a script both as a module and a main entry point. And let's see here how this. So this is the module here, and I have there's a special variable defined when you import a module. And name here, if you do an import, this code will be executed in the module actually. So when you import, the code of the module will be executed. So if you have a print statement and do an import of this module, it will print out the name of the module and define the function. So it will actually execute the code. So if I import that, let's see, just going to download those here. You can see here that the print statement prints out, but I downloaded a file called prime_extra.py, which I import, which prints out this here when I import it. But if I want to run this, if I run the prime extra from the command line, for example, if you're not in a notebook, you type Python and the source code file, but you can simulate this in notebook using run and the prime extra here. So if I run this, it prints out something else. It prints out main. If I run a script with a Python interpreter or do run in the notebook, it is considered to be the entry point of your execution. And that is tagged differently. So now this module is the main starting script of Python. And in this way, you can define kind of a main function. So in this case here, I have my module, I have import file. This is a main Python file. To protect it from being to kind of do different things depending if it's imported or if it's run as a main script. I can do if main equals to main. Then I do this. So this is done if I start this script from the command line as the main script. This is executed. If I import this, import prime main will be prime main, and this will not be executed. So in this way, you can have source code that can be used both as a module and as a main program. It's nothing preventing you from having a main program without this here. But if you try to import this, it will run the code. So this is usually what you do when you want to define a main program in Python. Some people also do def main, and then you have an if statement which calls main to kind of get the kind of more common one that have a real main function. So here, if I do run prime, it will execute this code here, and if I import it here, no code will be executed because name equals to prime main in this case and not main. So if you come look at Python code, you usually will see with the main script has this kind of if statement. So this is very common in many starting points of Python codes. Should we do a 10-minute break and then continue afterwards? So let's continue here. Something that also you need when you are coding in Python is a way to format output in a nice way. For example, if you want to print floating point or anything, you would like to control how you print it. The print statement has ways you can comma separate things and print it out, but you don't have really very good control. So in Python, there is the notion of formatting format strings. And what you can do is you can use a method on the string called .format, and you give it a string, which is the template of what you want to print out. And then you give it, so the placeholders here are curly brackets. So every curly bracket pair here will be correspond to one of the parameters going in here. The comma and spaces here are your formatting. So this is what you want to add to your formatting. So this can be anything, but the curly brackets are the numbers. So if I run this one here, you can see here that it takes the values from the variables here and places them and replaces the curly bracket with the values here. And it adds comma space, comma space, comma space, like that. You can also change the ordering. So if you want them in a different order, you can specify a number here to say that the first parameter should go here, so reverse the order. That's not the most common way of doing it. You can also do, so we start with strings. For example, I want to print a string, but I want it to be 15 characters in width at least. Then I can say here I have :15, that is the field width. Curly brackets, you can have parameters in front of that as well now, but now we don't have any. The last parameter is the field width. I put larger and less than here to kind of indicate how the string is placed inside here. So if I run this, you can see here I have a string here that is I'm going to start on the left side here. The number of characters here is 15, and it places this one and adds spaces here so that it fills up 15 characters. So this can be good if you want to do tables with a fixed number of fields with certain widths. If you want the string to be right-sided formatted, so by default it goes on the left side. If you want it to be on the right side, you can add greater than here. So you can say that it's an arrow that points on the side that you want to format it to. So I know this one. So now you can see it pushes Python to the right. You can also do centering by using the raised the certain text character here, and that will center the text in the field. So now you can see it will be there were spaces, add spaces to the left and right of the field. You can format integers. Then you give the B character here. And you can specify here the field width with an integer with a field width of 10. And then you can use the same operators here to actually center it on the left or right side. But you can also specify that which character to fill out empty spaces with. So in this case here, I can underscore, I can fill out with zeros. So here you can see I have 10 characters. This is formatted to the right, the left, centered, and then I have a fifth character here of underscore, and I can have a fifth character of zeros to the top. That's it. Floating points is a bit more complicated. You specify field width and the number of decimal places. F here is a fixed format, so no scientific notation. What that becomes. So you can see here 2 decimals, 4 decimals, and 6 decimals, and the total field width of 10. Then I can add, if I want to have it on the left side, I have to have a special for screens. I don't know the reasoning for that, but and then you can have scientific notation. Well, the same rules here. Then you need to add something to field width here to add for this extra character here. I think there is a general, I think as well. There is a J here, but that will try to do the least character floating point representation. So if it can't fit, it will try scientific notation, but it will default to fixed, but fixed form will never go to scientific station, this will switch. If I add up to something. Okay. You can also have name placeholders. So if you have variable with names here, you can give them as names here inside the template. And then it's also possible to have a dictionary with key value pairs. And then you can specify the keys here. And then you have to give it a certain, this kind of strange notation here. Star parents, and then it will replace the values in the dictionary in the curly brackets here. You can also do, there is a special function in Python called globals, which contains a dictionary of all the variables in your current context. And then you can give that as an input here, then you can use the variable names in your code directly. I will add, there is also a new way of doing it, which I will add after this lecture here with using formatting strings. It's similar to this one here. Another thing that is basic kind of knowledge, the requirements for when you code is be able to read and write files. In Python, you create a special file object which you is used to communicate with the file. And you create this object using the open statement. And it has two parameters, the open function. So first is the file name you want to open. And then what operation you want to do. So W here stands for write, so we'll create a new file. And then it returns to an object here, text file. And it's through this object that we will operate on the file. So now it will create a file. I think it's already created here. If you look here, my file is currently empty. So now we need to operate on the file, and the text file object has methods that we can use. And the main method for writing the file is .write. And then you just give it strings that we want to write to the file. The thing is that write will not do a new line by default as a print statement. So if you want a new line, you need to have a backup end in your write statement. So this will kind of be one line. This will continue on this line here. This will be a new line. And this will, they will print two lines here in the file. Then, important thing when you are done with writing to or reading files for that matter, you need to close the file. So you have the file method close. That tells the operating system that we are done working with the file, and it will write it down to disk. Because many operating systems they actually don't write the file directly to disk. It goes to a cache, and for it to be more efficient and quick. So until you do close, it will kind of not do too much with it. But when you do close, you say, okay, it's fine to write it down to disk. In between there, it's uncertain. So then we do close, and we can type the file here and see what happens. So now you can see the contents of the file we created. So file, you can see here, this was a single statement, this was another statement, and here is a new line, and then we have the next statement. Reading from file is the same procedure. You need to create a file object, but you specify, instead of W, you specify read, R for read. And now the file must exist, otherwise you get complaints. So if I do try to open, for example, my file 2 here, file not found. So I need to make sure that the file exists. And now I have a text file object. And now we have multiple options for handling reading. One really simple one is just to do content equals to text file read. That will read the entire contents of the file into a string. It's perhaps not the It works well for smaller files, but if suppose you have a 5 GB file, you don't want to have a 5 GB string. So it's not optimal in every case, but it's nice to have that option. I do close again, and then you see here I have my content here. This string is now the contents of the file. Usually when you have longer file, you read, at least text file, you read line by line. And then you open the text file here for reading. And then we can do statement called read line. It reads one line to a \n character, stores that in a string. And if you are at the end of the file, this string will be empty. So you can use a while statement if the while line is not empty. We can print that line and then we read another line. So should that be empty, it will not go to the next step here. And then we run the loop. So now you can see here that it prints out first line and then the second. But why do we have an extra space in there? Yeah, so we read in the line which will contain the new line character. And then we print which adds a new line character. We have two new line characters. So first we have the line, new line character, then the print, so that we get an extra here. So if we want to fix that, we can use some of the method I told you about last time here. We can use rstrip to remove any extra stuff from the string. So read line rstrip to remove any trading character like the new line here. And we do the same thing here in the inside the while loop. And now it will read correctly and print it out line by line. Yeah, exactly. Yeah. And then there's actually really cool things as well here. So you can see there's a lot of ways of doing things in Python here. You have the option of using a for statement to loop over the text file. So you can do for line in text file. That will read line by line through the text file. That depends on if you need the line count or something. You want to kind of be more sophisticated. I think this is usually, easy to read. And I think it's more efficient as well. I'm not 100% sure. If you have reasonable sized files, you can also use the read lines here to read the file into a list of lines, which you then can process offline. In this case here, you get list here that contains every line, which then you can iterate over later. If you don't want to if you want to make sure that you close your files when you are using them, you can use a special statement in Python to guarantee that. So there is a new statement called with. So with open as text file, with guarantees to call close in this file. So you just have to open here and do the operations on the file, and after here, this will automatically call close on the file. So it can be used for example, if you have network connections as well, you can use with here to ensure that you close the network connection, for example. So this is a nice way of guaranteeing that you have call close on this. Then you can do something also that's important, is error handling. So you should try when your code defensive. So make sure that the file exists before, and if it doesn't exist, print a nice error message yourself. Don't rely on Python to do an exception, because users don't probably like exceptions. So here's an example here. I can do a special module called OS. The OS.path exists, file name that will return true if that file name here exists. Then do with open as text file, otherwise print file. So this is one way of doing error checking using if statements. So here you can see, instead of having an exception here, I get my file. But there is another way of handling exceptions as well. So if you run this code, for example, you get this horrible error here, which you shouldn't present to your users. You should kind of, if you have your own code, you should present your own error messages. This here is something called an exception. So every time Python has an error condition, it throws an error message which is called an exception. And this is the exception name here. And what we can do to catch those is we can use a special construct called try. So try will execute the code in this code block here. If any exception occurs, or it will go to the except section here. This construct here will catch any exception, so it's not recommended, because if you do this in your own code, you will never see an error messages. You just execute them. Oh, everything's fine. Because you catch everything. So in this case, any error will produce feeling couldn't open us. But it illustrates the concept here. So my field.text doesn't exist. If I do this, you see feeling couldn't open us. But you can specify exactly what exceptions you want to handle by specifying a name. So if you get an error exception when you run the code, you can look at the name, you can put the name here. So try except find not found error. You only, this will be printed if this exception occurs. Other exceptions will be kind of shown in the normal way in Python. You will get this error message, but you can handle those, but you can't handle yourself. In this case, it will find not found. You can also add more exceptions here. So there is a lot of exceptions in Python you can handle. So here you have find not found, permissions error, for example, if you can't open the file because of Unix files permissions. If it couldn't convert it to a floating point, you have a value error. You can listen like this. You can also get some additional information from your exceptions. So because an exception is an object in Python which is thrown to your code, you can hash the object here. So except file found as E. E will be the exception object, and then you can use that to query, for example, which file name. So the exception has a property called file name. So you can actually see which file name we have an exception. And you can also have the actual error string using E.string error here. So you can get out the error message from the exception as well. Here you can see this here is from the exception object. Sometimes you want to ensure that some code is executed regardless of the exceptions. So here I have I open two files, I do my processing here, and if it finds some error, it will print it out. But it will ensure here, finally here, there's a special clause here. This will always be executed, regardless of you have an exception on it. So if you want to have a complicated processing thing here, and you know that you need to do some cleanup afterwards, you can put finally, and it will always execute that. So you can see here. Yeah, you can see stäng öppna filer här. This is always called, regardless of you get all these error messages here. So that is a way of kind of catching the final thing before shutting the light on before you leave. So I wanted to show you, I mean, you don't have to focus too much on this in this course now in the beginning, but you know, if you need to make your code more robust, go into here and look at the exception parts. So that was the introduction to Python. Now I'm going to switch over to NumPy. Not think I'm going to do everything managed today, but most. So NumPy. So up until now, we have been using the built-in functions of Python, and lists and lists of lists is not suitable for doing array computing. You need something else that is more efficient. And NumPy is not part of the runtime library of Python. It's an external project, which is part of Anaconda. It's built into the Anaconda part, but you can also download it separately. And it handles arrays of large arrays of the same data types. So you can have vectors and matrices consisting of thousands of elements of the same data type. And it's very efficient to handle that. And also the normal Python data structures are flexible, but too slow for numeric operations. So how do you use NumPy? Yeah, this is the standard convention of importing NumPy. So you will see this a lot in code on the web. So you import NumPy, which is the module NumPy, as NP. And NumPy is a binary module in Python. So let's import that. The basic data type of NumPy is the array object. And it handles large chunks of values of the same type very efficiently. So let's start by creating really small array types. So you create an array using NT009F, and then you can give it the data that it should contain, and then you specify the data type as well. So here you can see that we need to specify the data type, at least indirectly. So if we don't specify that, it will deduce it from the list here. But it's always a good idea I want to have a floating point array, and then it will convert those integers to floating point values. So if I run this code, you can see it's this is floating point here. So all the values in the array will have the same data type. It can also be smart. So if you give it an array with integers, it will create an integer array. So the data type of this will be integer. All of the elements will be integer. Also, you can't have the flexibility of a list that you can mix and match strings and floating point values in an array. It's always the same data type in the entire array. So if we give a floating point here as well. You can do multi-dimensional arrays. Then you use the HP calculator way of specifying arrays. So you give a bracket, and then this is the first row, this is the second row. So you give it lists of lists in Python. So this will be a square array with 1, 2, 3, and 4. And this will be 2 rows and 4 columns. That's okay. And you can see this will, because of specified integers here, the data type will be integer here as well. And you see that it knows about the dimensions here. When you print out, it will print out in the shape of the array as well. Something that you should know about is that when you create arrays, the data of the arrays, the numbers, is actually not stored in a 2-dimensional way in the memory of the computer. So when you allocate an array of 100 elements, 10 by 10, it will be stored in a linear fashion in memory with 100 elements. The rows and columns are kind of just a construct. In this case here, we have an array with shape 6 by 5. So the values here in that array is stored like this. So it's stored row by row. So in memory, it will go like this. But actual storage in computer memory is like that. 13390, and let's start this row here 25384. This also means that as long as you don't change the number of elements in the array, you can change the shape of the array, the number of arrays and columns. You can make it flat from 6 by 5 to 30, for example, without reallocating the values. And NumPy uses the C way of storing arrays. So C and C++ store them row-wise like this. When they come to mixed language programming, Fortran does it in column-wise. So it uses this way of storing instead. And NumPy supports us as well. So you can tell NumPy to use Fortran storage scheme so that you can pass arrays over to Fortran, which is important. You can, when you have great array objects, there are properties on object. You can go querying the shape of the array. So dot shape is a tuple that contains the shape of the array. So if you look here, we have one-dimensional array. The shape is 4. Two-dimensional array, you have 2 by 2, and you have a three-dimensional array, you have 2 by 2 by 4. So that contains the shape of the array object. You can also use it, for example, if you quickly want to have the rows and columns in variables, you can do r, c equals to b.shape. And that will assign r the number of rows and the c the number of columns. There is also a property that the number of dimensions of the array here, so ndim, which shows a property here. So b is 2 dimensions. So there's a lot of built-in extra information in the array object. And there's even more information here. So you have D type, which is the data type allocated for array. So that for every cell, this is the data type. The number of elements in the array, so size. And the item size here, that is the sizing bytes of each item of the array. So a floating point usually is 8 bytes. An integer is 4, I think. So in this case, it should be 4. No, 8. It's longer integer. So 8 bytes integers here. Array size is 4, with the 4 elements. Data type is integer 64. That's why we have 8 here. And then the 2 dimensions, and then this shape, rows and columns. You can change the shape of the array. This is just a function here to illustrate where the memory is located for the array. So it's a bit complicated, but it's interesting is that what you can use memory of it will return a memory location of the array. So in this case here we have A, 2-dimensional, and we print the memory of A where it's located in memory. Then we do A flat, empty, reshape A, over, so make it flat. And then we query the memory of that as well. I forgot to press that one. That's a problem with notebooks, that you need to execute them step by step. If you forget a step, your other code with cells will fail. So you can see here that the memory location here is just a unique number here, but it's 848 at the end. We reshape it, it's still 848. So reshaping does not change the memory allocated for the array. So this way you can go from 2 by 2 to 4 by 1 here in one step without reallocating. And that is, you can see that in NumPy it goes to great lengths to avoid reallocating, because it's a heavy operation, especially if you have millions of cells. So changing values in an array, you use brackets here, 0, 0. So this is row 0, column 0. So NumPy is 0-based compared to MATLAB, which is 1-based. You need to kind of get that. It's easy to make mistakes if you copy MATLAB code to Python code and you don't think about this. So if I change it here, you will see now that I wrote 0, 0 in A, but you can see A flat also changed. The same memory location. So it works this way. If you don't want that, you already covered that with lists. You can do C equals A.copy. Then we do the same thing here between C. Print out the memory location of C. You can see here that 84 here, 42 still there, but now we have a new memory location of C, but with the same contents of A. Initially, then modify C. But potentially copy can be a costly operation, so you should be a bit careful about when you want to use that. Some more examples here. We have the array here, 2 rows. We can reshape that to one-dimensional array with 8. We can have reshape it to 4 by 2. So we change the thing here. But just so you know, this is not the same thing as transposing an array. So this will just reshape it and preserve the numbers. They will happen in the order they were created in memory. So this is 1, 2, 3, 4, 5, 6, 7, 8. And here you see it 1, 2, 3, 4, 5, 6, 7, 8. And here is the actual transpose of the matrix, which is NT009F, which is not the same as a reshape of the given array. No, so this is a new array that points to the same memory location of this one with a different shape. So they point to the same values, but with a different shape. So if you do this, the number of items must be the same. We have 8 here, 8 there, and 8 there. But they are interpreted, so you can have different views of the same data structure. This is a transpose, which is different. I think also that is, if you look at okay, I managed to do that as well. I thought it would do something with the transpose, but it didn't. So, but this is it's not the same operation. You can change the size of an array. Then you have the resize operation here, resize, and then you give a new size. And what happens then is it will take the existing values and just fill it out with those values. And now we are reallocating. So here you can see we have existing array, and then we do a 9 by 9. It just fills it up with the existing values. 4 by 4, same thing. 4 by 2 here. So resize is reallocated. So in the previous examples here, Kendo is not suitable for creating large arrays. So if you want to create large arrays, we need some functions to kind of pre-fill them with data. And NumPy uses mostly the same syntax as map. So if you want to create an array with zeros, you empty zeros and you give a shape 4 by 4, and then you will see here that you get an array of zeros. By default, it will use floating points. You can specify the data type here as well. Then it will do integer array with zeros, like that. You also have a function called ones, which works in the same way, but you get floating ones instead of zeros. And you can use that to create arrays filled with a single value. So empty ones, 5 by 10, floating point. So now this is ones, and if you multiply it with 42, every value will be 42. You can see here, arrays support the multiplication operator, and that will be element-wise operations on all of the elements in the array. You can also create, use similar to the range function in Python. You can use there's a corresponding function called array range or a range, which will create an array from 0 to 9. But now it's an array object. It's not a list. And you can use that to quickly reshape. If you want an array of 10 by 10 starting from 0 to 99, you can do every range. You reshape on that one to 10 by 10, and then you get an array that is 10 by 10 filled with values going from 0 to 99. You can also have a range that starts from -10 to 10. You can specify the data type. Just like the Python list. You can have your step length here as well. And you see this is floating point, and this will be integer. You can also create identity arrays. So with the ones on the diagonal, so you do np.identity. You can see here you have ones here. I think you can also specify, if I'm not mistaken. No. I thought you could do that. Yes. You can specify the data type there as well. A ranges is not suitable. If you want to do a range, for example, for plotting values in a matplot function or something, you shouldn't use a range. You should use something called linspace instead. So this will create. Here you have a starting point value and the value. Both of those are included in the final range, and then you say I want 10 values. But then it will interpolate between those, and it creates an X range here that is more suitable for putting into plotting functions and so on. And this will create 20 values instead of the same range here. So you can see it interpolates here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. 0 is included and 1 is. And here we have the same thing, but 20 values and starting ending. If you have used the MATLAB, you have this colon notation when you're plotting with a step thing. So this can be seen as the corresponding method of creating the same kind of ranges. So array expressions. So you've already seen one. We did the 42. We multiply 42 on the array. So NumPy arrays can do operations array to array, array to scalar, scalar to array. So now let's create simple A here. You can add a scalar, integer, for example. That will add 3 to all elements in the array. And this is implemented in C, so it's very fast. So it's much faster than doing loops. As I said before, if you can avoid loops, it's a very good idea, especially in Python. You can do multiplication. You can do call mathematical functions on every element in the array. So there's NP has sin, cos, all basic math function implemented, but all of those can operate on arrays. So this will call the sign function of every value in this range in the array and return a corresponding array. You can do negation, that will negate all values in the array. And you can also add 2 arrays together. Sizes does not have to be the same. So we are not talking about matrices now, we're talking arrays. And so we can add two matrices together that are different sizes. So we have an A array and a B array here. And we add them together, it will kind of just add B on top of all elements in the B array. Matrix multiplication. So the normal multiplication operator for arrays is element-wise multiplication. If you want to do matrix operations, you need to use a different operator or a method. So the AND operator here is matrix multiplication. You can also use A dot A to do the same thing. But if you want to do matrix operations, it's probably better to create more readable expressions in that sense. So this is matrix multiplication. I think we will do this last part here, but then we stop. You can also, as I said before, we can access elements using different notations. So you can use the list notation here, 1 and 2, also this 1, 2, to access the elements. You can do assignment, the same thing. But you can also extract, just like we do with lists, slices of arrays. And if you do start and the same thing here, you know the end is not included here, it's n-1. You can do start colon, and all values. So for example, if you have A is a long range, you want 1 to 5, you get a sub-array here that is from 1 to 5. And one thing that is interesting here, when you do this, as I said before, NumPy will try to not recreate memory or copy memory. So if we create one radio, memory array, and then we do this one, and we look at the memory of B, and see what they contain here. So you can see that the memory function we have, so that's because they are pointing to different memory locations. But you can actually see the data here is actually allocated memory. And you can see here that both A and B are the same memory. So even if there are different slices, the memory of B that we extracted here is still part of the same memory allocation in memory in the computer. In that way, there is no copying being done here, which we don't want. And then you can do stuff like this. So all elements except the last two, last elements of A, and also you can do in reverse order here, colon, -1. And you can do multidimensional things. You can, for example, all rows in column 0, you can do all rows in column 0 and 1, all rows in rows 0, rows 0 to 1, last row, for example. So you have a lot of powerful indexing here for accessing your array. Like this. And also, it's possible to mix. So if we assign, for example, this is an array, the second row here with a list, so it's automatically translated into array. So those values in the list will be assigned. You don't have to have an array object here. You can mix lists to assign arrays. Same thing here. Here I assign the column number 3. These values here from a list, and it will work perfectly. This will not be converted to a list, but it will use the list to assign elements into the array. You can see here we assign first here, then here. I think we continue for the next lecture with matplotlib. I put up the first assignment in Canvas as well with things here, and you can, all materials is available if you want to continue here. Most of the things are here. Okay.